All right, folks, we are on lesson 13 of our pre-calculus statistics unit. So let's get going. Example 1, ducks at the charity carnival. One game that is popular at some carnivals and amusement parks involves selecting a floating plastic duck at random from a pond full of ducks. In most cases, the letter S, M, or L appears on the bottom of the duck, signifying that the winner receives a small, medium, or large prize, respectively. The duck is then returned to the pond for the next game. Although the prizes are typically toys and crafts, suppose that the monetary values of the prizes are as follows. Small is 50 cents, medium is $1.50, and large is $5. The probabilities of winning an item on a one duck selection are as follows. Small 60%, medium 30%, and large 10%. Suppose a person plays the game 4 times. What is the expected monetary value of the prizes won? So that's what we're looking at today. What is the expected monetary value of the prizes won? We're going to work through this in a couple of different steps and just kind of see where we go from there. So let's say that capital X is our variable. It's our discrete random variable. It's representing the monetary value of the prize that you win playing this game one time in dollars. And we're going to complete the table below and calculate the expected value of X. So just as we have in the past, right, we've listed every value of that discrete random variable. In this case, our values are 50 cents, $1.50, and $5. We've also listed the probability of X, so 60% chance that we're going to get small, 30% chance that we're going to get medium, and a 10% chance that we're going to get large. So we're going to fill in this final column here. Using a calculator, we can multiply the event, which is the amount of money, times the probability. So 50 cents times a 60% chance would give us 0.30. $1.50 times a 30% chance would give us 0.45. And $5 times a 10% chance is going to give us 50 cents. So adding those all together, 0.3 plus 0.45 plus 0.5 gives us a sum of 125, and that's in dollars. That's our expected value when we play this game one time. Right? The expected value, if I play this game one time, on average, I would be winning $1.25 each time I play this game. So number 2 asks, regarding the expected value that you computed above, could you win exactly that amount on any one play of the game? Could we win $1.50 on could we win $1.25 on just one play of that game? And the answer is no, right? Like when I look back up here, there are only 3 prizes, and none of those prizes give us $1.25. So no, the expected value is $1.25, which is not one of our 3 outcomes. And we've talked about this quite a bit, right? We have an expected value that talks about a long run average. It's not about what we expect to get on a singular play of the game, but on average, if this game was played an abundant number of times, and we divided by that abundant number, we would expect to get $1.25 each time you play the game. So I want you to take a minute and calculate this next bit. What is the least you could win in 4 attempts? And what is the most you could win in 4 attempts of this game? So I'm going to pause right here. Okay, so hopefully you took a look at the small event, and the small event is 50 cents. And when you multiply 50 cents by 4, you would get that the least you could win in 4 attempts is $2. And the most that we could win in 4 attempts, hopefully you took a look at that large amount. And if you won a large all 4 times, you multiply that by 4, the most we could get is $20. Okay, so the least we could get in 4 attempts is $2. The most we could win in 4 attempts is $20. How much might we expect to win in 4 attempts if this is the range that we're given? So let's go ahead and turn the page. Okay, I'd like you to write down your thought process to answer these questions. How would you explain the expected value in context to someone who had never heard of this measurement? Maybe you're going to use the sentence frame that we've used in class a number of times. And then the second question is, what would you expect for the total monetary value of your prizes from 4 attempts at this game? And I don't want you to list all the outcomes for 4 events of this game. I'd like you just to think about it. If your lowest range would be $2, your highest range would be $20, what would we expect to get in 4 attempts at this game? Or maybe use that expected value calculation that we just did. So take a minute, pause, and answer these questions. All right, so maybe you used that sentence frame that we had from before. If a large number of blank were observed, oops, there should be a number here, of blank were observed, we would expect an average of about blank blank. And this was our sentence frame from before. We've used this in class a number of times. If a large number of, maybe we're looking at this carnival game, right? We're looking at the carnival game, the duck game. So if we were looking at a large number of duck games, we would expect an average of about $1.25, 1 per game, something like this. That could be a way to explain the expected value in context. And actually, for the second question, what would you expect for the total monetary value of your prizes from 4 attempts at this game? An easy kind of calculation that we could do is we could say, well, we expect $1.25 for 1 game. If we were playing 4 games, I might expect to get $1.25 each time, so I might multiply this by 4. And if I take $1.25 and I multiply it by 4, I would expect to win $5 in total. Something like this. So we have this little paragraph below. Maybe get out your highlighter, because we've been using our highlighters to talk about important vocabulary terms and concepts in statistics. So the question above gets at an important feature of expected value. If the probability distribution remains the same for each trial, also called independent trials, we talked about that word independent, you can determine the expected value for n trials by computing the expected value of 1 trial and multiplying that expected value by n. You don't have to develop a complicated probability distribution covering all the results of all n trials, and this rule makes it far easier to compute expected value for situations where several hundred independent trials occur, such as a carnival or a lottery. So over the past couple days, we've been creating probability distributions that have, maybe there were 3 eggs or there were 4 defective tires. Imagine doing that for hundreds and hundreds of trials. That would take a lot of paper. So instead, we're gonna learn this shortcut over the next couple pages. So example 2. In a laboratory experiment, 3 mice will be placed in a simple maze, one at a time. In the maze, there is one decision point where the mouse can turn either left or right. When the first mouse arrives at the decision point, the direction the mouse chooses is recorded. The same is done for the second and the third mouse. The researchers conducting the experiment add food in the simple maze. such that the long-run relative frequency of each mouse turning left is believed to be 0.7 or 70%. So if we were just looking at one mouse, we're defining the random variable, which is x, right, which is how many left turns we're expecting to see. And we're going to complete our table using multiplication. Now, this multiplication is pretty simple because all I'm doing is multiplying 1 times 0.7 and 0 times 0.3. So x times the probability of x1 times 0.7 is 0.7. And 0 times 0.3 is 0. So the sum is just 0.7. We would expect to see 0.7 left turns. Now again, that doesn't really make a whole lot of sense if we're just talking about one mouse. But if we observed lots and lots and lots of mice making a decision, we would expect on average 0.7 left turns per mouse. So let's determine the expected value of left turns for 3 mice. For 3 mice. So if we use that same strategy from above, I can just take that expected value for 1 mouse, which was 0.7 left turns, and multiply that expected value by 3. And 0.7 times 3, if you'd like to use a calculator, you can. Maybe you've got this one on lock. We would expect 2.1 left turns from 3 mice. Now again, we're not going to actually observe 2.1 left turns. It only makes sense to talk about left turns in terms of whole numbers. But 2.1 left turns is our long run average of left turns that we would expect if we viewed a large number of sets of 3 mice. Okay, so let's turn the page and let's see if that expected value shows up in the same way if we used the strategy that we've been using in other class periods, which was listing every outcome, creating a relative frequency table, and then calculating the expected value. Let's see if it turns out the same way. So let's turn the page. And what's nice is that they've actually given us all of the outcomes. They've organized their thinking in a tree diagram, but for us, the thing that we're looking at is this outcome column, right? So there's 8 outcomes when there are 3 mice, because each mouse has 2 possibles. It has a left or a right, a left or a right, a left or a right. So 2 times 2 times 2, 8 outcomes. LLL, LLR, LRL, LRR, RLL, RLR, RRL, RRR. Right? And we're seeing over here on the right that we're doing all these calculations. A 70% chance that we'll see a left turn and a 30% chance that we'll see a right turn. So we can make all of this, we can assemble all of this data into a relative frequency table. So I'm gonna zoom out just a little bit so we can see that relative frequency table at the bottom, and let's start to fill it in. So first, 3 lefts is only from this one outcome. There's only one outcome that has 3 lefts, and so that's why its probability is 0.343. There's only one outcome when there are 0 lefts, which is our last outcome, RRR, and that's where the 0.027 comes from. But there's some more outcomes that we need to look at. There's some outcomes where we have 2 lefts, which is this outcome here, and this outcome here. There are 3 of those, right? 3 of our outcomes have 2 left turns. So what I need to do is I need to add together 0.147 plus 0.147 plus 0.147 to fill in the probability of getting 2 left turns. So let's go ahead and do that over to the side. I'm going to add together 0.147 plus 0.147 plus 0.147. It probably would have been faster if I just multiplied 0.147 times 3. And I can fill in my table. So the probability that we're going to see 2 left turns out of 3 mice would be 0.441. And then lastly, we have the probability of just having 1 left turn, which is going to happen here and here and here, right? 1 left and 2 rights. So we're going to add together 0.063 plus 0.063 plus 0.063 for a total of 0.189. So before I do my expected value calculation, I'm just going to do a quick check that when I sum these numbers together, I should get, hopefully you said 1. So we're going to add together 0.343 plus 0.441 plus 0.189 plus 0.027, and we do get exactly 1. So that's a good check for us before we calculate the expected value. I am going to pause here, and I'm going to have you do that calculator work. So pause here, get working on that expected value, and we'll come back. Okay, hopefully you had a little bit of work time. Let's go through these calculations together. So I'm going to multiply 3 times 0.343, and I get 1.029. I'm not going to round right now because I want to be as exact as I can. 2 times 0.441, I get 0.882. 1 times 0.189, and because of our identity for multiplication, we get that same number. 0 times 0.027 is 0. So now it's time to sum these numbers together. 1.029 plus 0.882 plus 0.189. Oh my goodness. Why does that number look so familiar? Pause for a second and talk to your partner. What do you think? Okay, so on this page, we found the expected number of left turns for 3 mice. We found that that number was 2.1. On the last page, if you flip back really quickly, we also found the expected number of left turns for 3 mice, and we said that that was 2.1. We found it a different way, though. We found the expected value for 1 mouse, and we multiplied it by 3. That got us 2.1. On this page, we found all of the outcomes for 3 mice, and we found the expected value for 3 mice, which was 2.1. So we found the same number 2 different ways. But maybe you're noticing that one of those ways was significantly fewer steps than the other. Okay? But in part B, we're verifying, yes, we agree that the expected number of left turns for 3 mice is the same as 3 times the expected number of left turns for 1 mouse, right? So this calculation was on this page. This was on page 95. We got 2.1. And this calculation was on the last page, page 94, and we also got 2.1. So we got the same calculation by finding the expected number of left turns for 3 mice. That's the same thing as 3 times the expected number of left turns for 1 mouse. So let's go ahead and apply that knowledge to the next page, right? And go ahead and work this one out on your own. Imagine that 200 mice are sent through the maze, one at a time. And the researchers believe that the probability of a mouse turning left due to the food is 0.7 or 70%. How many left turns would they expect from 200 mice? All right, hopefully you got to this point and realized that you didn't have to list all of the outcomes for 200 mice. You realized that I could just take my expected value and multiply it by 200. And if I do my work on a calculator, 0.7 times 200, that I would expect 140 left turns. That would be my expected value, my long run average. Okay. Example 3 brings us sort of back to example 1, but I want you to pay careful attention to example 3, even if you want to highlight this one in a special color, because this is an example that's going to help us out when we're thinking about our unit project. Our unit project, which I'll introduce after spring break. But for right now, just know that you are going to be creating a carnival game where you will need to have someone, buy in. We're going to use fake money. Someone's going to buy in. They're going to play your game, and they might receive, money back, or they might lose. There's lots of different outcomes that you could create to your game. But getting started thinking about that here in example 3. So we're revisiting the charity carnival of example 1. We recall that when selecting a duck, the average monetary value of the prizes you win per game was $1.25, right? That was our expected value in example 1. But how can the charity running the carnival make any money if it's paying out $1.25 to each player on average for each game? To address this, in most cases, a player must pay to play a game, and that's where the charity or any other group running such a game would earn its money. Imagine that the cost, this is going to be important for us, the cost to play the game is $2. What are the expected net earnings for the charity? What are the expected net winnings for a player? So let's go ahead and just start by calculating the player's net earnings for small, medium, and large. And I'm just going to go ahead and write them out like this. We'll start with small, medium, and large. And I just kind of want to remember, what do they cost? So I'm going to flip back a couple pages and just take a look. How much do each of these things cost? Small was 50 cents, medium was $1.50, and large was $5. So let's go ahead and write that down. Small was 50 cents, medium was $1.50, and large was $5. So when I'm saying I need you to compute a player's net earnings, what that means is if the cost to play the game was $2, we're subtracting $2 from each of these options. So the net winnings, if a player paid $2 but only won 50 cents, then net they lost $1.50. If for the medium prize they paid $2 and they won $1.50, that means net they lost 50 cents. And for a large prize, if they paid $2 but they won $5, that means that they earned $3, right? So there's actually only one of these outcomes with a positive net earnings. And so that's kind of what it's talking about in number 10. For 2 of the outcomes, the net earnings result is negative. What does a negative value of net earnings mean in context as far as the player is concerned? So if the player has a negative net outcome, it means that the player has lost money on the game, right? The player has lost money. The player lost money on the game. Okay. So let's, with these three values, and I'm going to go ahead and highlight them, with small being negative $1.50, with medium being negative 50 cents, and with large being positive $3. Let's go ahead and fill in this table down here with y being the net amount that we win or lose. So small would be negative 1.5 or $1.50. Medium would be negative 0.5, negative 50 cents. And large would be positive $3. So go ahead, I'm going to pause here. I want you to calculate the expected net earnings for this game. All right, let's make sure that we've got these calculations on lock. So 1.5, but I'm making it negative, times 0.6 is negative 0.9. Medium, which is negative 50 cents, times our 30% chance is negative 0.15. And large, 3 times 0.1 is 0.3. So if I add all of these numbers together, negative 0.9 plus negative 0.5, negative 1.5, excuse me, plus 0.3, on average, we should be losing 75 cents every time we play this game if the buy-in to play this game was $2. Okay, so you can put a $sign in front of that. It's a little bit funky, right, to see a $sign and then a negative, but we'll let it be. All right, last page. How would you explain this expected value in context to someone who had never heard of this measurement? Write a sentence explaining this value from the perspective of a player. Then write a sentence explaining this value from the perspective of the charity running the game. So go ahead and use that expected value sentence frame, and then we'll come back in a bit. All right, if a large number of blank were observed, we would expect an average of about blank. And I'm just going to kind of color code this sentence. If a large number of, we're playing this duck game, right? That is our game that we're playing. We're going to start from the perspective of a player. If a large number of duck games were observed, we would expect an average of about, and I might say 75 cents lost by the player per game. That's one way of framing this, right? If I'm saying that the player wins negative 75 cents, then on average, our player is losing 75 cents each game. But if I'm writing this from the perspective of the charity running the game, I might say if a large number of duck games were observed, we would expect an average of about 75 cents, not lost by the player, but won by the charity or received by the charity per game. So it's all a matter of perspective. And again, to kind of zoom out and look forward, when you all are creating your game for our project for this unit, I want you to keep in mind that you as the game master, you should be having a goal of winning the most money. So thinking about an expected value that works in your favor as the person hosting the game. Okay, so go ahead and make this quick last calculation. How much money should the charity expect to earn from the game being played 100 times? Okay, so if we expect that the charity is earning 75 cents each time this game is being played, and we play this game 100 times, then we should expect that the charity earns $75 in total. Okay, so putting that all together, let's go ahead and flip the page for your summary sentence. Okay, so your summary sentence, there's lots of sentences actually on this one. By computing the expected value for the earnings from a game of chance, one can determine the expected average payoff per game. When this value is positive, the player can expect to come out ahead in the long run. However, in most games of chance, this value is negative and represents how much the group operating the game takes in on average per game. From a player's perspective, a negative expected value means that the player is expected to lose that amount on average with each trial. Businesses and establishments that intend to make money from players are counting on situations where the player's expected value is negative. And if you've ever heard this phrase that the house always wins, that's often how casinos make their money, is that they have expected values that are created in favor of whoever's operating the game. And then our last summary sentence, as long as the probabilities remain the same for each instance of a game or trial, you can compute the expected value of n games as n times the expected value of one game. So let's putting it all together. Lesson 13, we have one more lesson to go in this unit, and then we'll review and take our unit test. Thanks for sticking with me.